In this video, we're going to look at using the properties of integration to evaluate integrals. Here we have example 2. Suppose the integral from 0 to 1 of f of x dx is 4, and the integral from 0 to 1 of g of x dx is negative 2. Find the integral from 0 to 1 of 3 times f of x dx. Using the properties of integration, we know that 3 times the function is going to scale that function 3 times taller. That would be the same as the integral of f of x dx from 0 to 1 times 3. Knowing that the integral of 0 to 1 of f of x dx is 4, 3 times 4 is 12. The next expression, the integral from 0 to 1 of the quantity f of x minus g of x. We know we can break up that integral into the difference of two integrals. The integral from 0 to 1 of f of x dx minus the integral from 0 to 1 of g of x dx. Using the values for those two expressions, we know the first expression is 4. We're going to subtract from that the second value of the integral from 0 to 1 of g of x, which is negative 2. So 4 minus a negative 2 is a positive 6. Example C, the integral from 0 to 1 of the quantity 3 times f of x plus 2 times g of x. Okay, we know we can break this up into 3 times f of x, the integral of 3 times f of x, plus the integral of 2 times g of x. Coefficients, vertical scaling is happening. We can pull those coefficients out in front. And simplify the expression by plugging in the values for each integral. So we're going to have 3 times 4 plus 2 times negative 2. That's 12 minus 4, or 8. Okay, there are actually 2 more examples here. In example D, D is very similar to C, except we have a difference instead of a sum. I'm going to jump right to breaking up the difference and pulling out the coefficients or the scale factors. So we're going to have 2 times the integral of g of x dx from 0 to 1 minus 3 times the integral of f of x dx from 0 to 1. Evaluating for the known values of those integrals, we get 2 times negative 2 minus 3 times 4. That's a negative 4 minus 12, or negative 16. All right, last example, E. We have the integral from 0 to 1. The limits of integration have been swapped from what we normally have seen from 0 to 1. We know that we could rewrite this as the integral from 0 to 1 of 2 f of x dx if we make this a negative integral. Okay, we can pull that 2 out in front, so that's a negative 2 integral from 0 to 1 of f of x dx. Negative 2 times 4 is negative 8. All right, example 3, we have the integral from a to b of f of x dx is 5. I don't know what this function looks like. I don't know what that area looks like, but I know the area under that curve between the interval from a to b, or on the interval from a to b, is 5 units. Likewise, for g of x, the integral from a to b of g of x is negative 4. Again, I don't know what those functions look like. I just know the area under the curve between a and b. Use properties to evaluate each of the following. So the integral from b to a of f of x dx is the same as the negative integral from a to b of f of x dx. So our answer is negative 5. 3 times the integral of f of x dx from a to b is equivalent to the integral from a to b of 3 times f of x. So we're pulling that coefficient out in front. That's 3 times a positive 5, or 15. C says the integral from a to b of 3 dx. There is no f of x or g of x reference in this integrand. This is the integral of a constant. The integral of a constant is just 3 times b minus a. Since they didn't give me values for b and a, I'm going to have to leave it in that expression form. Question D is combining a constant plus a function. So it's like we're combining example C and, well, just the simple given f of x. So we can break this up into the integral from a to b of 3 dx plus the integral from a to b of f of x dx. That's going to be 3 times b minus a plus 5. Question E, the integral from a to b of the quantity f of x plus g of x. We can break that up into 2 different integrals. The integral of f of x plus the integral of g of x. Adding the 2 known quantities together, we have 5 minus 4, or 1. Okay, letter F. Here we have the difference of f of x minus g of x on the integral from a to b. So we're looking at the integral from a to b of f of x dx minus the integral from a to b of g of x dx. Using the known quantities, we have 5 minus a negative 4, or 9. Okay, the last expression says the integral from a to 6 of g of x plus the integral from 6 to b of g of x. So the only thing we need to assume in order to answer this question is that 6 is on the interval a to b. All right, and if that is the case, we are looking at adding those 2 integrals together and getting the integral from a to b of g of x dx, which is just negative 4. Okay, examples 4, 5, and 6. If the integral from 2 to 5 of 2 f of x plus 3 dx is 17, find the integral of f of x dx from 2 to 5. Okay, and this is independent of the example 3 f of x dx integrals that were given up above. So let's just break this up, use the properties, and see what we get. So we're going to have 2 times the integral from 2 to 5 of f of x dx plus the integral from 2 to 5 of 3 dx, and we know this is equal to 17. Okay, so I see that the question is asking me to find what this expression is equal to. And now I see that expression in my equation. So we can just continue solving. And we know the integral from 2 to 5 of 3 dx is going to be 3 times 5 minus 2, or 3 times 3, which is 9. And we just have a little algebra to do here. We are going to subtract 9 from each side. Right, and then we're going to divide by 2. And so the integral from 2 to 5 of f of x dx is 4. Okay, question 5. If f of x is an even function, okay, we need to remember what an even function is. An even function has symmetry. This is not a function, but it has symmetry to the y-axis. That means that every f of x value is equal to every f of negative x value. Okay, so it says f of x is an even function, and on the interval from 0 to 4, we know that the area under the curve is 6. Now, not that I know what f of x looks like, but I know it's an even function. So it could be as simple as that function, just as an example. But if we know that the area under the curve from 0 to 4 is 6, and we know the function is even, then we know the area from negative 4 to 0 must also be 6. Therefore, the integral from negative 4 to 4 of f of x dx is equal to twice the integral from 0 to 4 of f of x dx. So the total area is 12. Okay, in question 6, we need to know what an odd function is. We need to remember that. An odd function has symmetry to the origin. So if the function is odd, there is symmetry to the origin. That's the same as a double reflection or a 180-degree rotation. That means that every f of x value is equal to the negative of negative f of x. Sorry, the negative of f of negative x. Sometimes it's also written as negative f of x is equal to f of negative x. Either of these are the definition of an odd function. Okay, so let's just pretend we have an odd function that looks something like this. We know that the integral from 0 to 4, or the area under the curve, is 6. That means the area in this triangle in the third quadrant is also 6, but that area is going to be negative if we look at the area from 0 to 4. So what is the integral from negative 4 to 4 of f of x dx? It's going to be the integral from 0 to 4 of f of x dx. Plus the integral from negative 4 to 0 of f of x dx. But we know this is positive 6, and this is negative 6. So the area under the curve is 0. Okay, I have one more slide, but we will do that in the next video.